A lot of that other stuff is just practice, but we're running out of time, so. All right, so we are integrating from 0 to 1 of x times x squared plus 1 cubed. So we're going to do it two ways. One way is the way that you guys have been doing it, and another way is a little bit shorter. All right, so based off of that, what would your u function be? Right. So then du would be 2x dx, correct? And what am I have to correct by a 1/2. Okay. So I know that I'm going to have 1/2 on the outside. I got du. And then I have u, right? So zero to 1, and then I have what, u cubed du. Okay, so that's going to become 1/2, right? And then 1/4 x squared plus 1 to the 4th. So you add, right, we're integrating u to the 4th, right? So this becomes to the 4th, right? You divide by your new exponent, and I'm just plugging u back in. Right, and we're going to evaluate that from 0 to 1. All right, because the reason I have to plug this back in is because these upper and lower bounds are with respect to x, right? So when you plug them in, your function has to be in terms of x. You can't leave it in terms of u. All right, so when I do that, when I plug in 1, I get 2 to the 4th is 16, divided by 4 is 4, minus 1/4. Okay, so if you want to multiply this to here, make it 1/8, you can do that too if you want. Mm-hmm. Right. So this is 4 minus 1/4. So what is that? That is 15 over 4. So you get 15 over 8. Yeah, you can do that. All right, now there's another way to do it, which I feel is a little bit easier and a little bit quicker than doing it the way that we just did, plugging the actual function of what we said u was back in. All right, so 0 to 1. Okay, so this is going to stay the same. U is x squared plus 1. Du is 2x dx. 1/2 du is equal to x dx. Right? Everything that stays the same. All right, so these upper and this lower bound are in terms, they go with x. All right, but if it's a little bit easier than having to plug this function back in, what I can do is actually leave my entire integrand in terms of u. All right, so you're going to have, if I'm going to replace, I have the 1/2 on the outside, right? I have u cubed du, right? So what my goal is that I don't want to plug this function back in. I just want to deal with it in terms of u now. So I'm just going to be integrating u to the third power. All right? Now, in order for this to work, I have to now change my upper and my lower bounds so that they are also in terms of u. All right? So this is in terms of x, and that's in terms of x. All right? So we want to change the upper and the lower bounds. So when x is equal to 0, u is going to be what? 1. Okay? And then I'm going to do this down here. When x is equal to 1, u is going to be what? 2. So your upper bound would then be 2. Yeah, so like 0 is, since it's on the bottom, the u is going to, this term is going to go on the bottom. This is on the top. This is going to go on the top. All right? So now what we can do is we can just integrate this. Now we don't have to plug x squared plus 1 back in. Okay? So I get 1/2, right? 1/4 u to the 4th from 1 to 2. All right? You do not have to plug u back in because you've changed everything to be now in terms of u. All right? So that gives me 1/8. 2 to the 4th is 16 minus 1 to the 4th. And you get 15 over 8, which is what we got before. All right, so I feel, I mean, again, really your preference. But I feel like if you, what's that? Well, all right, so this is, again, this is kind of a simple example, but sometimes when you guys get more difficult functions, it might be a little bit easier to do, you know, to evaluate this function instead of this one, right? So if we had like e to the 5x squared plus 7, right? And if you just left it as e to the u, that's a lot easier to evaluate than e to the 5x squared plus 7. You know what I mean? So maybe not the best example to be using, but again, I think this method is kind of what you should practice getting in the habit of. So you have to remember that you need to change your upper and your lower bounds so that they are in terms of u. All right? All right, number 14 is from 0 to pi over 4 tangent of x times secant squared of x dx. Oh, Mike, I did that, the one that you were suggesting. Remember the other day we were debating? I worked it out. It does come out to be the same. It's a trig identity. So there's a third way to do. Yeah. Okay, so what would your u function be? Right. So it's probably easier if we use tangent as my u function because when you do your again, there's multiple ways you can do this one. Because if I take the derivative of tan, I get secant squared. Right. We had to use like a trig identity. We were like missing that. Okay, so I have u, I have du, right? Now I just have to change my my lower and my upper bounds, right? So when x is 0, u is going to be what? So again, you're plugging in 0 into there. So what is tangent of 0? 0. Now when x is pi over 4, u is what? So what's tangent of pi over 4? 1, right? So now changing everything around, I have 0 to 1 of u du. All right? That's a lot easier to work with. So my integrand would be 1/2 u squared going from 0 to 1. So I would get 1/2 minus 0, which is just 1/2. Now, if you plugged tangent back in, right, kept all the things the same, you would still get the same answer. But again, that's a lot easier if you just leave it in terms of u instead of plugging it back in for terms of x. All right, so when you are using u-substitution and it's a definite integral, you want to change your things around so you can keep it in terms of u. They're all just a little bit more complex. So, all right. How would you rewrite that one? Okay. All right. So my u function would be what? Du is 2x dx. So I'm off by 1/2. Okay, so, sorry? Oh, it should be 4. Thank you. All right, so when x is 0, u is going to be what? -4, good. And then when x is 1, u is going to be -3, right? All right, so does everyone understand where we're getting these values from? They're coming from here. When you plug in 0 into here, that's how you get the u-term. So we're going to go from, where do we go, -4 to -3, and then what would my integrand be? Du, and then I got the 1/2 out front. Okay, so antiderivative of u to the -1. So u replaces x squared minus 4, right? And then x dx is replaced by 1/2 du. So what do you get? Natural log of u going from -4 to -3. Well, if you add 1 to the exponent, right, you get 0. Right. So if you take the this is really like 1 over u, right? So what's the derivative of ln? Right. That's kind of just the rule for the antiderivative. All right, so I got ln of -3, right? Top minus the bottom. ln of -4. What does that come out to be? Right. Yep. All right, so we're not going to do them, but this would be 7a. All right, now there's no function when I take its derivative that's going to give me just plain tangent, right? But how could you rewrite that if you wanted to figure out the antiderivative? Right. Exactly. So it'd be sine of x times cosine of x to the -1. Right, so based off of that, what would your u function be? So then du would be negative sine of x dx. So I have negative du equals sine of x dx, right? So when I do my integrand now, I got negative integral of u to the -1 du. So what does that become? Right, negative ln absolute value of what? Cosine, right? Plus c. No, you don't have to memorize them. Right? So you would come up with the cotangent one the same way. Same idea. And then secant and cosecant are ridiculous. We're not even going to do them. Say again? Yeah. I wouldn't do that. All right, if you guys go to number 12, okay, so based off of that, right, we're just going to, just a separate problem. No, you can just use the space that's there. So I'm going to rewrite, right, x, 2x minus 1 to 1 half. All right, so what would your u function be? Right. Okay, so then du would be 2 dx, right? Okay, now, we have, exactly, there's no 2 there, and we have this x, right? This is another separate function, okay? So what I want to do is I want to put both of these in terms of u. Instead of them being in terms of x, I'm going to put them in terms of u. All right, so what that means is that I'm going to take what I've designated to be the u function, I'm going to solve that for x so that it tells me what x is equal to in terms of u. So if you have u is equal to 2x minus 1, right, I'm going to add the 1 and then divide by 2. So you got u plus 1 over 2 is equal to x, right? And what else do I want to do? So I'm going to put u in for here, and I'm going to put this here in for that. That'd be really, I think, more difficult than what it needs to be. Streets of Belmar are rough, you know. All right, so again, I want to put my constant over here on the other side as well. Okay. Right. Okay, so when I rewrite now, right, I have 1/2 integral. I'm going to replace the x term with u plus 1 over 2. And then I'm going to replace 2x minus 1 to the 1/2 with just u. All right, now everything is in terms of du, right? What else can I do? Right, so what would be out here? Right. Okay, how would you simplify that? We've already done u sub, so. Good. All right, now it's a simple power rule. And I'm going to take this. No. Mm-hmm. Okay, so I add 1 to my exponent, right? So that would be u to the 5/2 divided by my new exponent plus u to the 3/2 divided by my new exponent plus c. Okay, now, what do we know u is? There you go. So now just replace that back in. So you have 1 over 4 times 2 over 5, which is 1 over 10. I know that u is 2x minus 1, so the 5 halves, plus, what is that? That's 2 over 12, so that's 1 over 6. 2x minus 1 to the 3 halves. And then 1/4 times a constant is just a constant. So that would be your final answer. It's really any constant. I mean, whatever it wants. So some number times another number is just a third arbitrary number. All right, so again, you want to use this technique when, you know how like sometimes we're off by like a constant? This is when you're off by an actual function. Well, any constant divided by 4 is just another constant. Yeah, it's just a constant. Like they're not that worried about that part. No, because you're only gonna, if you see one question on your test, then it's a lot. I'll give you your